So the purpose of today's lecture is to cover a topic called approximate integration. In approximate integration, you can be on a desert island and get a fairly good estimate to an integral without having a calculator. You already have some form of approximate integration. When you use a Riemann sum, that is always an approximation to an integral. So there are other kinds of sums that better approximate a definite integral, and that's what we're going to talk about today. We're going to talk about two different approximations. One's called the trapezoidal rule, and the other is called Simpson's rule. So I will get started. So section 7.7, approximate integration. So let's talk about the trapezoidal rule first. So the idea is, first of all, to remember what a trapezoid, the area of a trapezoid is. So if you have a trapezoid, let's call the smaller height little h and the bigger height capital H, and let's call the base B. So the area of this is the base times the average height. In other words, the base times h plus capital H over 2, or if you put the 2 under the B, it would be B over 2 times H plus big H. Okay, so that's great. So that's the basic idea. And now what we do is, if we have a function, now I'm going to just for simplicity assume the function is non-negative on the interval AB. What you do is you're going to subdivide, that's poorly written. So in other words, so I'm going to let A be x0, and then I'll look at delta x is the size of the subdivision, so that would be B minus A over N. N is the number of intervals in the subdivision, and then you have x1 is less than A, x2, all the way up to xn, which is B, where xk, the kth term, and the subdivision is x0 plus k times delta x. So we have, here we go, x0, then we have x1, etc., right? And then B is xn. So maybe we have x2. Okay, so now if I try to, what I'm gonna do is I'm gonna draw dots, lines to the curve, etc. And then I'm going to connect the dots on the curve. Each time I connect a dot on the curve, I'm going to get a trapezoid if I connect these with straight segments. So we have the first trapezoid, we have the second trapezoid. So let's say the kth trapezoid is equal to, it's going to be given by the base over 2, so that's delta x over 2, times the little height, the sum of the two heights. Now the two heights are given by f of xk minus 1 plus f of xk. Okay, so then if we therefore the integral from a to b. By the way, let me just say the area of the kth trapezoid. Okay, so the integral from a to b of f of x dx is then approximately equal to summing up this expression. So it will be the sum. K goes from Let me, you know what? Let me re-index this. I'm going to re-index this slightly differently. So I'm going to put an xk here and an xk plus 1. So it's going to be the sum. K goes from 0, let me make black, to n minus 1, it turns out, is the right thing to do, of delta x over 2 times f of xk plus f of xk plus 1. So now you can rewrite this, and that's what I'm going to do, as delta x over 2 as times f of x0. Now there are going to be 2 copies of f of x1 that appear in the sum. Then there are going to be 2 copies of f of x2, and so on, all the way up to the next to last term, which will be 2 copies of f of xn minus 1, and then we have to add f of xn. Okay, so that is the expression you get. So that is called, that's the trapezoidal rule. So let me summarize what I did in a cleaner way, because it's getting cluttered, the screen. Okay, so let me make some room. Okay, so the trapezoidal rule says that Tn, which is the nth trapezoidal approximation, is given by delta x over, and it's the approximation to the integral, delta x over 2 times f of x0 plus twice f of x1 plus dot 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 plus twice f of xn minus 1 plus f of xn. So notice the coefficients that are in front of the f of xi's are 2, always 2, the coefficient, except in the first and last case. So now we can use this formula to approximate an integral. Let's just do an easy situation. So let's consider the case of y equals x squared, and we're going to choose, just for simplicity, n equals 4. So if n equals 4 and y equals x squared, and I'm going to let x vary from 0 to 1, just for fun. So here's 0 and here's 1, and then we have a quarter, we have 2 quarters or a half, and then we have 3 quarters, and then 1. It's a parabola. And now we have the various trapezoids that we're approximating by. Okay, so now what does the formula tell me? It tells me that, first of all, delta x in this case is a quarter, because 1 minus 0 over b minus a over n is 1 minus 0 over 4. And t sub 4 in this case will be delta x over 2, so that's 1/8 times f of x0. Now, x0 is 0, so you're going to get a 0 there. Then a quarter, we have to square 1 quarter, so that gives me 1/16. And then we have a half, we have to square that, so that's a quarter. Oh, by the way, we should put a 2 in front of these, right? So 2 times 1/16, 2 times a quarter. Then 3 quarters squared, which is 9/16 times 2. And then we have to evaluate at 1. F of 1 is 1, so we're going to get 1 here. And so if you do the arithmetic, if I did it correctly, this will give you 11 over 32 as the approximation. Now, actually, we can compare this to the actual integral of x squared, which we can always do directly, of course, in this case, which is x cubed over 3 from 0 to 1, and you get a 1/3. So the distinction between these two numbers is pretty close. 11/32 is very close to 1/3, which brings us to something called the error bound formula. which I'm going to talk about next. It's the error-bound formula for the difference between the nth approximation using the trapezoidal rule versus actually computing the integral directly. So let me clear the screen. So the error-bound formula for the trapezoidal rule goes like this. So let's consider, so suppose we can find an upper bound. Suppose for the second derivative, suppose f double prime of x, its absolute value is smaller than or equal to some number k on AB. Now, this is something that's special to the given function, and this is a number you have to find. It's not automatic that it's easiest to find such a number, but if the function has derivatives of all orders, such a number k exists, and you want to find the smallest number k, which does the job for you. And now let's set e sub t sub n equal to the integral from a to b of f of x dx minus the nth trapezoidal approximation. So then the result is the error is going to be this number here. The absolute value of this number is called the error. And this is given by the following expression. This is actually a theorem. This is something that one can prove later in this course. It's possible to do it. You take b minus a, raise it to the third power, multiply it by k, and divide it by 12n squared. So this is the so-called famous error-bound formula for the trapezoidal rule. So for example, in the case y equals x squared and n equals 4, then let's consider what the error-bound formula says there. So what is f double prime here? The first derivative of x squared is 2x, and the second derivative is 2. And that's a constant. So we can take k to be equal to 2 in this case. And then if we substitute it into the error-bound formula, et sub 4, absolute value is at most 2 times 1 minus 0 cubed over 12 times 4 squared. And that should give you, looks like 1 over 96. And in fact, in this case, the following is true. If we take the integral from a to b, well, we take the difference, the integral from a to b of x squared dx, and subtract off the trapezoidal approximation t sub 4, that's going to be 1/3 minus 11/32. And if you compute that, you actually all get exactly 1 over 96 in this case. Now, getting exactly the same answer in this case, that's just an accident. It's because this function y equals x squared is so simple. In general, you don't expect to get the same, the error bound to be sharp. In this case, it's a sharp estimate. The error is sharp in this case. Okay, so that's how the one way the error-bound formula can be used. I'm going to give you now another way the error-bound formula can be used. So here's an example of another way to use the error-bound formula. How large should n be so that t sub n, so that the error bound t sub n is, say, less than 0.001, which is 1 over 1,000. So, and then let's do this for the example. Let's do this in the case y equals x squared as before, and on 0, 0, 1, just like we did it before, just before. So how large do we need to take n so that the trapezoidal approximation is as close to the actual integral as we want it to be, in this case, within a difference of 0.001. And here's the solution. We take the error bound formula, so that's this. That's k times b minus a cubed over 12 n squared. And we want it to be, we demand that it be less than 1 over 1,000. So in this case, b equals 0, 1, and a equals 0. So in other words, we know k was 2, so this is going to be 2 times 1 minus 0. K is 2 because we're looking at y equals x squared. 1 minus 0 cubed over 12n squared, and we want that to be smaller than 1 over 1,000. So this is an inequality that we can easily solve. This is telling me that 1 over 6n squared should be less than or equal to 1,000. And then if we take the reciprocals, that's the same thing as 6n squared being greater than or equal to 1,000. So n squared should be greater than or equal to 1,000 over 6, which tells me that this tells me that n should be greater than or equal to 12.9 something. So in other words, n should be 13 because n is a whole number. So that's how you would solve that kind of problem. You have to solve an inequality, and that tells you how far you have to go to get an error, in this case, of less than 1 over 1,000. Very good. So in the second part of this lecture, I'm going to talk about Simpson's rule, which is very similar to the trapezoidal rule. It is a better approximation typically than the trapezoidal rule. It converges or gets closer to the answer faster. You don't have to take n as large. So the way this works, the idea here is to use parabolas instead of trapezoids. So suppose I have like a picture like this, right? So some curve on AB. Let me make this a little different. Suppose B is like here. Okay. So the idea is, let's just take a single point in between the midpoint, and then let's put in some subdivision points. Suppose we subdivided like this. So then we can graph these points. Let me do this in a different color. Okay. And then we can fill in between the first 3 points. 3 points which are not on a line determine a unique parabola. Just like 2 points determine a line, 3 points, if they're not in the straight line, determine a unique parabola. That you can easily see by solving equations. So here's a parabola that goes through the first 3 points. And then let's look at the last 3 points. It's going to be another parabola that approximates that. And then what we can do is we can take the area under this parabola, and we can take the area under the second parabola, that would be here, and add the areas up. So we add up the areas under the parabolas. Now, computing the area under a parabola is very, very simple if you know the formula for your parabola. You know, a parabola is of the form ax squared plus bx plus c, and you can easily integrate that. So, so what we're going to do is the following. Here's the setup. I probably should put this in black, so go back to the black color. So n will be even in this case. We need an even number of subdivision elements because, for example, we have 2 parabolas, and how many points do we have on the axis to work with? We have 1, 2, 3, 4, 5 points, but how many intervals? So this would be the 0th point. This would be x0, x1, x2, x3, x4. So here n would be 4 in this case. So I need n even in the Simpson rule. Okay, and I'm going to look again at a subdivision, a standard subdivision with n elements. So delta x is b minus a over n, and x sub k, the kth point in the subdivision, is x0 plus k times delta x, as we had with the trapezoidal rule. So now the Simpson's rule says this. So the Simpson's formula or Simpson's rule says nothing more than this, is that the integral from a to b of f of x dx, it looks similar in spirit, so we're going to call it's approximately equal to some sum I call Sn. This is the nth Simpson sum, nth Simpson approximation, and it's given by the following thing. We're going to take delta x, now it's over 3, and we're going to take the following thing, f of x0 plus 4 times f of x1 plus 2 times f of x2. It's going to alternate between 4 and 2 from now on. So it'll be 4 f of x3, then plus 2 f of x4, dot, 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 dot. And then the last term will be an f of xn, and the previous to last term is 4 times f of xn minus 1, and so on, dot, 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 dot. Okay, so that is the Simpson rule. Okay, so I'm gonna rewrite this because I've run out of space. So let me clear the screen. Okay, so the Simpson rule Sn is given by delta x over 3 times f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, and so on. It alternates, dot, 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 dot. And then we end up with twice f of xn minus 2 plus 4 times f of xn minus 1 plus f of xn. And that's the formula. Okay, and there's also an error-bound formula, the error-bound. So if we look at the difference between the integral from a to b of f of x dx minus Sn, we can call this E sub S sub n. That's the error bound. And the absolute value of the error is at most some number, let's call it k times b minus a to the 5th over 180 n to the 4th power, where k, now we don't use the second derivative, we use the 4th derivative of the function. And that should be bounded, absolute value bounded by k on the interval ab. So that's the error-bound formula. And this number is going to be typically smaller than the corresponding error-bound formula for the trapezoidal rule, because we're taking n to the 4th here, not n squared in the denominator. So let's do a simple example. So here's the example I have in mind. Let's let y equal 1 over x. 1 less than or equal to x less than or equal to 2. We want to approximate the integral from 1 to 2 of 1 over x dx, which we know, by the way, is ln of 2. That's the exact answer. Okay, so let's take n equals 4. That's an even number. And let's use the the Simpson approximation. So S4 is delta x over 3, so that's a quarter over 3. So now let me sketch out what this looks like. Here's 1 and here's 2. Here's the curve. It's a decreasing curve. And we have 1, which is 4 quarters, 5 quarters, 6 quarters, 7 quarters, and 8 quarters. These are the subdivision points. Okay, so that's the curve. These are the subdivision points. Okay, so okay. So then it's 1/4/3 times f of x0. Now x0 is 1, so it's 1/1, which is 1, plus 4 times f evaluated at x1. x1 is 5/4. So the function is the reciprocal function, so it's 4/5, plus 2 times the reciprocal of 6/4, which is 4/6, plus 4 times 4/7, plus 4/8, because 8/4, or 1/2 if you like. 4/8, 2 reciprocal is a half. Okay, and you can compute what this is on your calculator, and you get 0.6933 up to like 5 places. That's the exact answer. Okay, so that's the answer. Now, what is the actual ln of 2? ln of 2, which is exactly the integral, is actually 0.6931. This is actually very close. Now, we can use the error bound formula. We know how close it is by taking the difference, but suppose we didn't know how to compute the actual integral. We can use the error bound formula instead, and I'm going to do that for you. We have to compute the fourth derivative of 1/x. So y prime is negative x to the minus 2, y double prime is 2x to the minus 3, y triple prime is negative 6x to the minus 4, and the fourth derivative is equal to 24x to the minus 5. So that is a curve. That's 24/x to the fifth. This is decreasing everywhere on the interval 1 to 2. So it takes its maximum value at x equals 1. This curve is a decreasing curve, whatever it looks like. It looks like this. So it takes its maximum value at x equals 1, so it's less than or equal to 24 on the interval 1, 2. Okay, so what does that tell us? That tells us by the error bound formula, the error of S4 is less than or equal to k. It's less than or equal to k, which is 24, times 2 minus 1, that's b minus a to the fifth power, over 180 of times n to the fourth. N is 4, 4 to the fourth power. And you can work out what this number is. It's easy on a calculator, but you can do it by hand even. It's 0.0005. We know the error is within that amount, and that's a way to estimate the error. Okay, so there you have it. I mean, the only types of, all the problems in this section are of the kinds I've gone over. We can do a problem, how large does n have to be, with the Simpson rule to estimate something to be within 1/1000, just like we did with the trapezoidal rule. But it works the same way. You're just using a slightly different formula. So I don't think we need to do that here. Okay, so that's it for today.